So in this video, we're going to be looking at entropy, changes in entropy, how we can calculate a value for that change as well as actually explaining the change too. Now starting off, we know entropy, it has a symbol S, and we know it is a measure of the degree of disorder in a system itself. Now that's our exam answer, but what does that actually mean? Well, when we look at a reaction, there's two things that actually affect, of course, how fast the reaction happens or whether it happens in the first place or not. One of them is, of course, our particles, they need to collide with the correct amount of energy, and we say that that is the activation energy, right? Now the second thing is of course they need to collide in the correct orientation. Now of course the number of different ways particles can arrange themselves is dependent upon, of course, how much entropy they have, and we know that if they can arrange themselves in more ways, then they're more likely to actually arrange themselves in the correct way and so react. Now our entropy values are always going to be positive, and the reason why is because all particles will have some degree of disorder, regardless if they're a solid, liquid or a gas, whether they're just an atom on their own or whether they're a molecule or in a giant covalent lattice, giant ionic lattice, giant metallic lattice. Because particles, they're going to be in constant motion, they're going to be either vibrating on the spot or they're going to be moving somewhat in, like, let's say a liquid, or they could be moving quite chaotically like in a gas itself as well. Now in terms of entropy, we know these values are always going to be positive, but entropy change going from reactants to products, that is going to be variable. That could be positive or it could be negative, and it's dependent upon whether order is going to be increasing or decreasing, or disorder, which is the term we prefer in chemistry, is going to be increasing or decreasing across the reaction itself. Now let's say if I had a positive entropy change value, that means our system is becoming more disordered or less ordered. If I had a negative entropy change value, that means that the system is becoming more ordered or less disordered itself as well. So we know, of course, the higher the value of entropy, the greater the disorder is going to be. Now moving on, if we were to look at the factors that affect entropy, the first one is, of course, changes in state. We need to look at the state symbols very carefully in a reaction, because that will tell us, of course, first of all, is entropy changing, is it decreasing, is it increasing, and we need to be able to explain this in the exam as well. Now when we look at solids going to liquids, going to gas, entropy is actually going to increase. The amount of disorder, the amount of ways the particles can arrange themselves, is going to increase. And so if I were to look at, let's say, a solid where I'm looking at 4 or 5 particles in a solid, right, I'm going to look at 6 particles in this case over here. We know that, of course, we've got lots of order from year 7 chemistry, and of course these particles, they are still moving, they're vibrating on the spot, and so they will have still some entropy, but not loads. It's going to be a very small amount, a very small positive value. Now let's say if I were to melt this solid, right, what I would end up with is, of course, a liquid where the particles can arrange themselves in more ways, and normally we know liquids, they can take the shape of a container itself. Now, of course, entropy is increasing, the amount of disorder in the system is going to increase, and especially when we go from a liquid to a gas, it's going to increase the most because our particles actually are quite chaotic. They're going to be moving around quite fast, colliding with each other, but more importantly, they're going to be able to arrange themselves in loads of different ways, because of course in a gas we know that we've got our particles completely separate from one another, and they can arrange themselves in lots of different ways. Now if I look at this example here, I've got water, of course, which is a liquid, being boiled, and of course it evaporates to form steam. We know entropy is going to increase in this case, right? So how do I actually explain that in the exam? What do I need to say? Well, the first thing that we can say is that the entropy change is going to be positive because entropy is increasing. We've already established that from the state changes. How do we explain why in the exam? Well, we would say that the liquid becomes a gas and there is more disorder. Yeah, so that's how we answer that in an exam question. Just watch out for the state symbols. What about the next one, going from solid to aqueous? Well, let's say if I were to have, let's say, something like sodium chloride, or an ionic compound, or a compound that can obviously dissolve in water. Well, we've got a solid over here, which is sodium chloride, and sodium chloride will dissolve in water, and what will happen is we form sodium chloride aqueous, which is going to exist, to be honest, as sodium ions, which is sodium plus aqueous ions, as well as chloride ions, which are going to be aqueous as well. And we know from module 2 chemistry that these mobile ions, right, they can move about, and so they can arrange themselves in lots of different ways, as well as conduct electricity as well. They're mobile charge carriers, yes, but they're also going to be able to move themselves about in lots of different ways. And we actually prefer to do our reactions in solutions because gases are quite hard to control, but solutions themselves, they're quite easy to control, and you can normally do them in something like a beaker or a test tube or a conical flask or something like that. Now, how would we go about wording this in the exam? Well, we would need to say the following: that entropy change is positive because, of course, entropy increases going from solid to aqueous. Why is that the case? Because the solid becomes aqueous and the aqueous particles are more disordered than solid particles itself. So yeah, looking at the next one then, we've got sulfur dioxide, but 2 lots of it, and then oxygen, 1 lot of it, to form 2 lots of sulfur trioxide itself. Now, of course, let's say if the states are all going to be the same, and you're looking at the number of gas moles in this case, you can see, of course, they're all gases, but we've got 3 moles of gas going to form 2 moles of gas. Now we can see the number of moles of gas is going to decrease. So of course we've got the same number of atoms on each side, but in the case on the left we've got more molecules itself. And so because we've got more molecules with the same number of atoms, we know of course entropy is going to be higher for the side with more molecules for the same number of atoms. So of course entropy in this case is going to decrease because we're going from 3 moles to 2 moles, 3 molecules to 2 molecules. So how would we actually describe that in the exam? We know of course entropy change is going to be negative because entropy is decreasing. We've got 3 moles of gas going to 2 moles of gas, therefore our system is becoming more ordered itself. And that is how we answer that one itself. Now, how can we actually calculate a delta S value? Well, what we can do is we can take, of course, the sum of all the entropies of our products and subtract the sum of all of the entropies of our reactants. And so basically what we're doing is just products minus reactants. A way I like to remember it is I like to put entropy change is S, delta S, and then I'm going to do products minus reactants, and that kind of spells out the acronym SPAR. Now the units of entropy, it's going to be different to enthalpy because enthalpy is normally given to us in kilojoules per mole. In the case of entropy, we've got joules per Kelvin per mole. So just be careful if the exam questions ask you to answer things in, let's say, kilojoules, then you know you need to divide by 1,000 somewhere. Now looking at this first example here, we've got of course delta S. We need to calculate a value for it in kilojoules per Kelvin per mole. So we know of course once we calculate delta S, we need to divide by 1,000. So if I were to look at this reaction, I've got the Haber process, and I'm just going to do products minus reactants. So we know delta S is going to be equal to, and then of course my products, which is going to be ammonia, but I've got 2 lots over here. So I'm going to have 2 lots of 193. So in brackets, I'm going to have 2 times 193 itself. And then of course, I'm going to subtract my reactants. I'm going to use some big brackets here. I've got 3 lots of hydrogen. So 3 times hydrogen, which is of course 131. And then I'm going to add that to nitrogen, which is going to be 192 itself. Of course, if I put that in my calculator, I end up with the following, which is 199 but negative, and the units so far is going to be joules per Kelvin per mole itself. Now of course we need to get that into proper units that the examiners actually asked for. It can change every time, but delta S in that case would therefore be minus 199 divided by 1,000, and so I end up with a value of minus 0.199 itself, and that's going to be kilojoules per Kelvin per mole itself. So we know of course our entropy change value is negative, so we know the amount of disorder is going to increase in this case. Moving on, feel free to pause the video and have a go at the following. So yeah, here we're asked to calculate the entropy change, delta S, the standard enthalpy change value in joules per mole per Kelvin. So we don't need to change any units over here. For the following reaction, we've got a table with some results and of course our balanced equation as well. So of course we know we're just going to do delta S. Of course we're going to do products minus reactants. We've got SPAR again. So in that case, I'm going to do my products, which in this case is going to be methanol. That's going to have a value of 239.7, not using big brackets here because it's really not needed. And then I'm going to use big brackets for the second part over here where I've got 2 lots of course hydrogen. So I'm going to do 2 times by 130.6, and then I'm going to add that to my value of carbon dioxide, which is going to be 197.6 itself. So there's these 3 values used up. Of course I'll put this in my calculator and I end up with the following answer of minus 219.1, and of course it's going to be joules per Kelvin per mole as well. So yeah, there's my answer for that one. Now, how would I actually know that this is the right answer? Well, most of the time you can pretty much estimate if it's going to be positive or negative, because this question is actually from the exam, multiple choice, where you've got positive 219.1 and then negative 219.1 as well. Of course, you can see you've got 3 moles of gas going to form 1 mole of liquid. So you know entropy for definite, the entropy change is going to be negative itself, because order is increasing, disorder is decreasing. Yeah. So yeah, moving on to the next question then. Feel free to pause the video and have a go again. So yeah, we've got hydrogen reacts with carbon disulfide as shown below, and the standard entropies are shown in the table as well. We've been given the actual entropy change in this case from what we can see. We haven't been given the actual entropy values for all of our reactants and products. We've got one missing, which is hydrogen, and we're asked to find the standard entropy for hydrogen in joules per Kelvin per mole. Now, of course, if we look at this, how I would go about it is I'll just make my equation as normal, put in a missing value as x, and then just rearrange it to find my answer. So in this case, delta S is minus 164, and of course that's joules per Kelvin per mole. Just make sure all the units match up as well. If it was kilojoules, I'd have to convert it to, of course, joules. So yeah, that's going to be equal to my products, which in this case is 2 lots of hydrogen sulfide, which is 206. So I'm going to use big brackets here, 206 times by 2. And then that's going to be added to methane, which is 186. That's that one done over there. And then, of course, I'm going to close these brackets. And then I'm going to subtract my reactants, which, of course, we've got carbon sulfide or carbon disulfide, which is 238. And we've got 1 lot of that, so that's minus 238. And then, of course, we've got 4 lots of hydrogen. So I'm going to add 4 lots of X there itself as well. Now, of course, the first thing that I'm going to do is I'm going to simplify everything that I've got so far. And that leaves me with 164 being equal to 360 subtract 4x itself. Now, of course, I'm going to move the 4x to the other side just to make things a bit more simpler in terms of rearranging. Of course, I could just go about it to find minus x, but I'm going to end up with adding 4x to either side. So I end up with 4x minus 164 is equal to 360. And then if I were to move the minus 164 to either side, of course, I would add 164 to either side, and I end up with 524. So 4x ends up being equal to 524. And then, of course, x would therefore be equal to that divided by 4, which ends up being a value of 131 itself. So we know we've got x being equal to 131. So the actual value for the entropy, the standard entropy of hydrogen, has been equal to 131, and it's going to be joules per Kelvin per mole, of course. And there's our answer there.